We've had a look at electric potential energy. Now let's see if we can get an idea about electric potential. To begin with, let's look a bit more closely at the analogy between gravity and electric charge. So we'll talk about gravity and then we'll talk about electric charge and how the two situations are very, very analogous. First of all, the force due to gravity and the force due to an electrostatic field are both equal to some constant. In this case, it's the gravitational constant, big G. In this case, it's Coulomb's constant, 1 over 4 pi epsilon naught, which we're just calling K. But the constant multiplied by the two interacting objects, the two masses in this case, or the two charges in this case, where Q1 is the charge causing the field and Q2 is the little test charge, both divided by the square of the distance between their centers. In other words, inversely proportional to the inverse square of their distances. The potential energy of both systems, of each system, is equal to a constant. In the case of gravity, universal gravitational constant and Coulomb constant, multiplied again by the two interacting particles, the charges or the masses, divided by the distance between their centers, or inversely proportional to the distance between their centers. You may not recognize these two equations immediately, but these are from the mechanics side of the AP Physics equation sheet. This is equation number 30. This is Newton's law of universal gravitation, and this is the equation for potential energy due to the gravitational force of some massive object. Now, just in case there's any confusion at all, I want to make clear that the electric field strength can be expressed as kq over r squared. And we derive this equation from equation number 2 on the AP equation sheet. So deriving this equation, we have the magnitude of the electric field, or the electric field strength, is equal to the electric force, the electrostatic force, divided by the charge. And we know that this Fe, this electrostatic force, is expressed by Coulomb's law. So here's Coulomb's law right here. Fe equals kq1q2 divided by r squared, and then divided by the charge, and the two charges cancel, and this Q2 is usually, well, it's always the test charge, and so we end up with kq over r squared. So that's just to clear up any confusion about this version of kq over r squared. Now, going back to our gravitational analogy, if we think of the gravitational potential energy per unit of mass, we've got the idea of gravitational potential. On Earth, gravitational potential energy is equal to the mass times little g, acceleration due to gravity, times the height above Earth's surface. So if we divided both sides by the mass, so not universal, but gravitational potential energy divided by unit of mass, so potential energy per mass unit, the mass divides out and we just end up with this little gh. So that's the idea of gravitational potential. So on Earth's surface, that's like lifting the 5-kilogram bowling ball up 5 meters of stairs to the second floor. But what if we wanted to know a more general idea of mass potential or gravitational potential? So instead of thinking of only moving the bowling ball and having its height change by 5 meters, to calculate the bowling ball's change in gravitational potential energy by dividing out the mass and just ending up with the GH, we get a general expression for potential that does not depend on the object. So just little g, acceleration due to gravity, times height, gives us this idea of gravitational potential, or mass potential, you might think of it. The units of mass potential are joules per kilogram. So potential energy is in joules and mass, of course, is in kilograms. So joules per kilogram. Now, it's not really done, but imagine that you know, for example, that the bowling ball has a mass of 5 kilograms, and just say that you happen to know that the bowling ball had 10 joules per kilogram of potential at that particular location. Well, what you could do with that is you could say, well, it's got 10 joules per kilogram of potential energy, and it's got 5 kilograms of mass. Well, it's got 50 joules of gravitational potential energy. Now, I mean, it's not really done, this way of calculating or thinking about potential energy or mass potential, but it could be done. You know, if you knew that it had 50 joules, if you knew that it had 10 joules per kilogram of potential at that particular location, then you'd know that it had 50 joules of gravitational potential energy. And so now let's treat the electric potential energy the same. Let's take the electric potential energy and divide out the charge. In this case, it's the little test charge. So electric potential energy is equal to kQ1, Q2 over R. Let's divide out Q2, the test charge, and what we're left with is electric potential energy per unit of charge, the same way that we divided out mass from gravitational potential energy. Now, instead of having mass potential, we have electric potential. The electric potential is the work that must be done to move a charge against the electric force, moving that charge from a reference point to a final point divided by the charge magnitude. The potential at a point in space is the result of all the other fields due to all the other charges close enough and big enough to contribute a force on that charge at that point. And so hopefully you recognize in this expression, equation number 6 from the AP Physics equation list. So this is Coulomb's constant. This is simply saying the sum of, so add up all the charges big enough and close enough to contribute a force on the charge we're talking about at that point in space. So all the charges divided by the distance. Okay, so the electric potential, strictly speaking, when you go to calculate it, it's just K times the sum of the charges if there's more than one. So the sum of the charges if there's more than one, divided by the distance between the charge causing the field and the reference point.